Hello there, and welcome to the Dreamy Science Guy. I'm glad you're here. Maybe it's been a long day, or maybe your mind just doesn't want to switch off yet. For the next little while, you don't have to do anything. No decisions, no to-do lists. Just let your body get comfortable, let your breathing slow down, and let my voice sit in the background like a quiet room light. In a moment, we'll drift into tonight's story. You can close your eyes, or just soften your gaze. There's nowhere else you need to be, and if you're still awake enough to move, I'd love to know where in the world you're listening from and what time it is for you right now. You can leave it in the comments so this little corner of the internet feels a bit more like a shared night sky. Mountains. They rise from the earth like the planet's architecture, built over millions and billions of years by forces so vast and patient, they make human timescales feel like heartbeats. These towering peaks and rolling ridges hold stories written in stone, stories of continents colliding, of ancient seas lifting into sky, of ice-carving valleys, and of life finding ways to thrive in the harshest places on Earth. They are the world's most dramatic sculptures, shaped by the invisible hand of geology and time. But beneath their grandeur lies something even more remarkable. Mountains are not static monuments. They are still moving, still growing, still being torn down grain by grain. They breathe with glaciers. They harbour ecosystems found nowhere else. They create weather, capture water, and shape the climate of entire continents. Some mountains are older than complex life itself, standing as witnesses to nearly the entire history of our planet. Others are youngsters in geological terms, still sharp and jagged, still reaching upward. Tonight, we'll wander through these vertical worlds at a pace fit for sleep. We'll trace their birth in the deep collision of tectonic plates. We'll stand in the presence of mountains so ancient they predate the Atlantic Ocean. We'll climb through invisible layers of climate and life, from warm forests to frozen tundra, all within a few thousand vertical meters. We'll watch glaciers carve valleys over thousands of years, and we'll understand how these massive features of stone can melt away in mere decades. Some of what you hear tonight may surprise you. Some may inspire quiet wonder. All of it will be delivered in a voice meant to accompany rest, not to demand attention. Let the words wash over you. Let your mind follow where it wishes. And if sleep finds you halfway through, that's exactly as it should be. And before we begin, if these gentle explorations into Earth's wonders help you unwind or give you a peaceful way to end your day, please consider liking this video and subscribing to the channel. It helps other sleepy souls discover this corner of calm, one restful night at a time. Now take a deep breath, settle in, and let's begin our journey into the mountains. Mountains begin not with a single moment of creation, but with movements so gradual that entire human civilizations could rise and fall, while a mountain range gains just a few meters of height. These peaks and ridges are born from the deep architecture of our planet, from the slow dance of tectonic plates that float on the Earth's semi-molten mantle, like enormous rafts of rock. The theory of plate tectonics, accepted by science only in the 1960s, revolutionized our understanding of how mountains form. Before this understanding, geologists struggled to explain why mountain ranges existed at all, why they appeared in certain places, and why their rock showed evidence of incredible compression and folding. The answer lay hidden beneath our feet, in the very structure of Earth's outer shell. The Earth's surface is broken into roughly a dozen large plates, and many smaller ones, all moving at speeds of just a few centimeters per year. That's about as fast as your fingernails grow. Yet over millions of years, these tiny movements add up to thousands of kilometers of travel. Plates collide, they slide past one another, they pull apart, and where they interact, mountains are born. The most dramatic mountains form where two continental plates collide head-on. Both plates carry continental crust, which is relatively light and buoyant compared to the denser oceanic crust. When these continents meet, neither can sink beneath the other. Instead, they crumple. Imagine pushing two thick rugs together on a hardwood floor. They fold, buckle, and pile up on each other. This is essentially what happens when continents collide, except the rugs are made of rock tens of kilometers thick, and the process takes tens of millions of years. The Himalayan mountains, Earth's highest range, formed exactly this way. About 50 million years ago, the Indian subcontinent, which had been drifting northward for millions of years after breaking away from ancient Gondwana, collided with the Eurasian plate. The collision was not sudden. It was a gradual pressing together that continues today. The force of India pushing into Eurasia compressed the rocks between them, folding and faulting the crust, thrusting layers of ancient seafloor thousands of meters into the air. Today, you can find marine fossils on the summit ridges of Himalayan peaks, limestone that formed on an ocean floor now standing at the top of the world. This process, called orogeny or mountain building, involves several mechanisms. Folding occurs when layers of rock bend under pressure, creating waves and curves in the Earth's crust. Some folds are gentle, barely noticeable. Others are dramatic, with layers tilted nearly vertical or even overturned completely. Faulting happens when the pressure becomes too great for the rock to bend, and it breaks instead. One section of crust slides over another along these fractures, sometimes for dozens of kilometers. In thrust faults, enormous slabs of rock are pushed up and over younger layers, stacking ancient rocks on top of younger ones in a sequence that seems to defy time itself. The Appalachian Mountains tell a similar story, but one that played out much earlier in Earth's history. About 480 million years ago, during the Ordovician period, the collision that would eventually form these mountains began. But the Appalachians we see today are not the mountains that first rose from that collision. Those original peaks may have rivaled the Himalayas in height, but they have since been worn down by hundreds of millions of years of erosion. Their sharp edges softened, their heights reduced. What remains are the deep roots of those ancient mountains, still impressive but nowhere near their former glory. Not all mountains form from continental collisions. Volcanic mountains rise from a different process entirely. When oceanic crust slides beneath continental crust in a process called subduction, the descending plate carries water and sediments down into the Earth's hot mantle. This water lowers the melting point of the mantle rock, causing it to melt and rise as magma. The magma, being less dense than the surrounding rock, pushes upward until it erupts at the surface, building volcanoes cone by cone, eruption by eruption. The Andes Mountains of South America form this way, as the Nazca Plate slides beneath the South American plate. The Andes are not a single line of volcanoes, but a complex range built from both volcanic activity and the compression of the continental crust above the subduction zone. Similarly, the Cascade Range in the Pacific Northwest of North America, home to peaks like Mount Rainier and Mount St. Helens, is a volcanic arc built above where the Juan de Fuca Plate descends beneath North America. Volcanic mountains can take different forms depending on the type of lava they erupt. Shield volcanoes like Mauna Loa in Hawaii form from fluid basaltic lava that flows easily and spreads out in thin layers. Each eruption adds a little more height and width, building a broad, gently sloping mountain that can grow enormous. Mauna Loa, measured from its base on the ocean floor, stands over 9,000 meters tall, making it one of the tallest mountains on Earth when measured from base to summit, even though its peak rises only about 4,000 meters above sea level. Stratovolcanoes, or composite volcanoes, form from thicker, more viscous lava mixed with ash and rock fragments. These volcanoes build steep-sided cones through alternating layers of lava flows and explosive eruptions. Mount Fuji in Japan, Mount Kilimanjaro in Africa, and Mount Rainier in Washington all fit this profile. They are among the world's most recognizable peaks, their symmetrical forms etched into human consciousness. Then there are mountains formed not by compression or volcanism, but by extension and breaking. When the Earth's crust is pulled apart, it can fracture along faults, with some blocks dropping down and others rising up. The blocks that rise become block mountains or fault block mountains. The Sierra Nevada range in California formed primarily this way. The range tilts gently westward, but on the eastern side it rises abruptly in a dramatic fault scarp, one of the steepest mountain fronts on any continent. Over millions of years, this block has been uplifted while the basin to the east, the Great Basin, dropped down. The basin and range province of the western United States showcases this type of mountain building on a grand scale. From eastern California to Utah, the landscape is shaped by parallel mountain ranges separated by flat valleys, all formed by the crust being pulled apart. Each range is a block tilted or uplifted along faults, and each basin is a block that dropped between them. This extension has stretched the crust, creating a landscape of alternating mountains and valleys that continues to evolve today. Mountains can even form from the erosion of plateaus. While this might seem counterintuitive, some mountains exist simply because everything around them has been worn away. These are called residual mountains. They were once part of a broad, elevated region, but over millions of years, rivers carved deep valleys into the plateau, leaving isolated peaks behind. The Black Hills of South Dakota and the mountains of the Colorado Plateau formed partly through this process, their heights maintained not by ongoing uplift, but by their resistance to erosion while surrounding rocks wore away more quickly. The timescales involved in mountain building are almost impossible to grasp intuitively. The Himalayas have been rising for 50 million years and continue to gain height at a rate of about 5 millimeters per year. That's barely the thickness of a few coins. But over a million years, that adds up to 5 kilometers of uplift. Of course, erosion acts at the same time, wearing the mountains down even as they rise, so the actual height gained is less than the total uplift. The highest peaks in the Himalayas, including Mount Everest, are still gaining elevation, though at rates that slow as erosion keeps pace with uplift. The relationship between uplift and erosion is complex and fascinating. In young, rapidly rising mountains like the Himalayas, uplift generally outpaces erosion, at least at the highest peaks. But in older mountains, erosion wins. The Appalachians, which may have once stood as tall as the Himalayas, have been worn down to rounded peaks and rolling ridges. Rivers have carved deep valleys through them. Ice ages have scraped and polished their surfaces. Wind and rain have broken down the rocks, grain by grain, carrying the sediment away to eventually deposit it on coastal plains and the ocean floor. The balance between uplift and erosion determines the ultimate height and shape of mountains. In humid climates with heavy rainfall, erosion is more rapid, and mountains may never reach the heights they would in drier climates. The Himalayas, despite receiving heavy monsoon rains on their southern slopes, continue to rise because the rate of uplift is so high. But if uplift were to stop, erosion would begin to dominate, and the mountains would start their long decline towards sea level. Different types of rocks erode at different rates, creating varied landscapes even within a single mountain range. Granite, being hard and resistant, erodes slowly and forms prominent peaks and cliffs. Limestone dissolves more readily in acidic water, forming caves and sinkholes. Shale, soft and easily broken down, erodes quickly, often forming slopes and valleys. This differential erosion creates the varied topography we see in mountains, with some areas steep and rocky while others are gentle and soil-covered. Mountain building is also influenced by the thickness and strength of the crust. Continental crust is thicker and more buoyant than oceanic crust, which is why continents stand higher. When two pieces of continental crust collide, neither wants to sink, so they crumple and thicken instead. This thickening can double the normal thickness of continental crust, creating a deep root beneath the mountains. This root, made of less dense crustal rock, helps support the weight of the mountains above, much like an iceberg floating in water with most of its mass below the surface. Isostasy is the principle that describes this balance. The crust and upper mantle float on the denser, more fluid mantle below. When mountains are built, the crust thickens and deepens, sinking into the mantle to compensate for the added weight above. When erosion removes material from the top of a mountain, the crust beneath rises, much like a ship rising in water as cargo is unloaded. This process, called isostatic rebound, means that even as mountains are eroded at the surface, the deep crustal root is slowly rising, bringing deeper rocks toward the surface. In this way, erosion and uplift are linked in a feedback loop that continues for millions of years after the tectonic forces that initially raised the mountains have ceased. In some cases, mountains rise not from horizontal compression, but from vertical uplift. The Colorado Plateau, for example, has been lifted bodily upward by about 2 kilometers over the past few million years. The cause is not fully understood, but it may be related to the sinking of the Farallon Plate beneath North America, which created thermal currents in the mantle that pushed the plateau upward. As the plateau rose, rivers like the Colorado River continued to flow across it, but now they had to cut downward to maintain their paths. The result is the Grand Canyon, a gorge more than a mile deep carved by the river into the rising plateau. The study of how mountains form has practical implications. Understanding the forces and processes involved helps geologists predict where earthquakes are likely to occur. It helps engineers design structures that can withstand the ground shaking that accompanies mountain building. It helps us understand the distribution of mineral resources, which are often concentrated in areas of past or present tectonic activity. And it helps us appreciate the dynamic nature of our planet. a world where solid rock flows like a thick fluid over geological time, and where the surface we stand on is constantly being reshaped. The forces involved are equally difficult to comprehend. The pressure needed to fold solid rock or thrust one slab of crust over another comes from the movement of entire continents. India continues to push into Eurasia, compressing the Tibetan Plateau and driving the Himalayas higher. The energy comes ultimately from heat in the Earth's interior, from the slow churning of the mantle driven by radioactive decay and residual heat from the planet's formation. This heat causes convection currents in the mantle, which drag the overlying plates along with them. We sometimes think of mountains as eternal and unchanging, but they are neither. Every mountain range on Earth is either growing or shrinking at any given moment. Young ranges like the Himalayas, Andes and Rockies are still actively rising, their rocks still being compressed and lifted. Old ranges like the Appalachians, Urals and Scandinavian mountains have stopped growing and are now purely in decline, slowly being levelled by wind, water, ice and time. Given enough time, all mountains return to plains. And then, given enough time, new mountains rise where old ones stood. This cycle has repeated many times in Earth's history. The Appalachians, ancient as they are not the first mountains to stand in their location. Earlier mountain building events raised peaks there before, only for them to erode away completely. The rocks that now form the Appalachians include some that were metamorphosed and folded in those even more ancient collisions. Mountains, it turns out, have a kind of memory, recording not just the collision that created them, but hints of collisions that came before. Understanding how mountains form gives us insight into the dynamic nature of our planet. The Earth is not a dead rock with a static surface. It is a living, breathing, evolving system where new crust forms at mid-ocean ridges, old crust descends at subduction zones, and continents drift across the globe, colliding and splitting apart in an endless dance. Mountains are the most visible evidence of this activity, monuments to the incredible forces at work beneath our feet. As you lie here tonight, resting in whatever place you call home, mountains somewhere are rising. They gain their height so slowly that no human could ever witness it in a lifetime. But they rise nonetheless, grain by grain, millimetre by millimetre, thrust upward by forces that operate on timescales measured in millions of years. They rise, and they will continue rising long after we're gone. Some mountains on Earth are older than almost anything else you can see with your eyes. They predate dinosaurs, predate complex life, predate even most of the oxygen in our atmosphere. These ancient peaks stand as monuments to a time when Earth looked nothing like it does today, when continents had different shapes and different names, when life clung to the edges of the sea and had not yet ventured onto land. The Barberton Mountains of South Africa, also called the Makonjwa Mountains, are believed to be the oldest mountain range on Earth. The rocks that compose them date back approximately 3.6 billion years, formed during the Archean Eon when Earth was still young and violent. At that time, the planet was being bombarded by asteroids, volcanic activity was intense, and the atmosphere contained almost no free oxygen. These rocks formed from ancient volcanic activity and sedimentation in one of Earth's earliest continental crusts. To put this in perspective, life itself may have just been emerging when these rocks formed. The oldest known fossils, microscopic evidence of simple single-celled organisms, come from rocks of similar age. When the Barberton Mountains took shape, there were no plants, no animals, no fungi. There were only microbes, possibly living in hot springs or deep in the ocean around hydrothermal vents. The world was an alien place, and these mountains have witnessed nearly the entire story of life's evolution on Earth. The rocks of the Barberton Greenstone Belt, as geologists call this region, are part of an ancient volcanic sequence. They include basalt, formed from lava flows, and sedimentary rocks like chert, deposited on an ancient seafloor. Some of these rocks show evidence of being pushed and deformed by tectonic forces, suggesting that plate tectonics, or something like it, was operating even in Earth's deep past. Studying these ancient rocks gives scientists a window into the early Earth, a time so remote that the geological record is sparse and fragmentary. The Guiana Highlands of South America, which include parts of Venezuela, Guyana, Brazil and Colombia, are estimated to be about 2 billion years old. These mountains are not towering peaks, but rather a series of flat-topped mountains called tepuis. These table mountains rise abruptly from the jungle, their summits hosting ecosystems that have been isolated for millions of years, evolving unique species found nowhere else. The rocks themselves are ancient sandstones and granites, part of a craton, a stable piece of ancient continental crust that has remained largely unchanged for billions of years. The tepui of the Guiana Highlands inspired Arthur Conan Doyle's novel The Lost World, and it's easy to see why. These isolated plateaus, surrounded by sheer cliffs hundreds of meters high, are like islands in the sky. Some have never been fully explored. The isolation has allowed evolution to run wild, creating endemic species of plants and animals that exist only on a single tepui. The geological age of these highlands places them among Earth's most ancient landscapes, formed when life was still confined to the oceans and the first photosynthetic bacteria were beginning to produce oxygen. The Hamersley Range in Western Australia dates back approximately 2.5 billion years. This range is significant not just for its age, but for what it reveals about Earth's history. The rocks here, part of the Hamersley Group, include some of the world's largest iron ore deposits. These formed during a period called the Great Oxidation Event, when photosynthetic organisms began producing oxygen in quantities large enough to react with dissolved iron in the oceans. The iron precipitated out, sinking to the seafloor and forming the banded iron formations that now make up much of the Hamersley Range. These rocks are a direct record of one of the most important transitions in Earth's history, the rise of oxygen in the atmosphere. The Appalachian Mountains, though not as old as these ancient ranges, are still remarkably ancient by most standards. The main mountain-building events that created the Appalachians occurred between 480 and 300 million years ago, during several collisions that eventually assembled the supercontinent Pangaea. The oldest rocks in the range, however, date back over 1 billion years, formed during even earlier geological events. The Appalachians stretch nearly 2,000 miles from Newfoundland in Canada to Alabama in the southern United States. At their peak, these mountains may have rivaled the Himalayas in height, but they have been worn down by hundreds of millions of years of erosion. Rivers have carved deep valleys through them, ice ages have sculpted their peaks, wind and rain have softened their profiles. What remains are rounded, forested mountains, beautiful but subdued compared to their former grandeur. The Appalachians hold a special place in geological history because they were part of a much larger mountain range. When Pangaea formed about 300 million years ago, the collision that created the Appalachians also created the Caledonian Mountains of Scandinavia, the Atlas Mountains of Morocco, and the Highlands of Scotland and Ireland. These were all part of a single continuous range called the Central Pangaean Mountains. When Pangaea began to break apart about 175 million years ago, this range split too, leaving fragments scattered across multiple continents. Today, if you compare the rocks and fossils of the Appalachians with those of the Scottish Highlands or the Atlas Mountains, you find striking similarities. They share rock types, structural features, and even some fossil species. They are geological relatives, separated by an ocean that opened where mountains once stood. The Atlantic Ocean is younger than the Appalachians. The mountains predate the ocean by hundreds of millions of years. The Ural Mountains, which divide Europe from Asia, are also ancient. They began forming about 250 to 300 million years ago during the collision that assembled Pangaea. For such an old range, the Urals reach surprising heights, with peaks over 1,800 meters. They are rich in minerals containing more than 1,000 different types, many of commercial importance. The Urals have been a source of iron, copper, gold, and precious stones for centuries, and their geological wealth comes from the complex processes of their formation. The age of these mountains has profound implications for life on Earth. During the time the Appalachians and Urals were forming, life was undergoing tremendous change. The first forests were spreading across the land, the first amphibians were crawling from the water, and the first reptiles were evolving. Insects had already diversified into many forms. The coal deposits that formed during this period, from the remains of vast swamp forests, now lie buried in the Appalachian foothills and other ancient mountain regions. The Appalachians are older than dinosaurs, when Tyrannosaurus rex walked the Earth. About 68 million years ago, the Appalachians were already ancient weathered mountains, much as they appear today. They had stood through the entire age of dinosaurs, watching as these great reptiles evolved, thrived, and went extinct. They stood through the rise of mammals, through ice ages and warm periods, through the evolution of humans. They are older than most of the stars we see in the night sky with our naked eyes, older than the rings of Saturn, older than the surface of Mars as we know it. Old mountains reveal something important about the nature of geological time. They show us that Earth's surface is temporary. Mountains rise and fall, oceans open and close, continents drift together and split apart. Given enough time, the landscape becomes unrecognizable. The mountains that seem so permanent to us, that have stood longer than human memory or even human existence, are merely passing features in Earth's much longer story. But old mountains also teach us about persistence. The Barberton Mountains have weathered nearly the entire history of Earth. They have survived billions of years of erosion, tectonic upheaval, and climate change. They have endured impacts from asteroids, the rise of oxygen in the atmosphere, snowball Earth periods when ice covered the globe, and countless other transformations. They are still here, still standing, their ancient rocks still holding secrets of the early Earth. When you think about the age of these mountains, consider what they represent. They are not just old rocks. They are archives, geological libraries containing information about Earth's distant past. Every layer, every fold, every crystal in their rocks tells part of the story. Scientists study these ancient mountains to understand how Earth evolved from a hot volcanic planet to the stable, life-bearing world we know today. They look for clues about when plate tectonics began, when life first appeared, when the atmosphere changed composition, and when continents first formed. The rocks of ancient mountains have witnessed unimaginable changes. The Barberton Mountains formed when the Earth was a completely different planet. The sun was younger and slightly dimmer. The moon was closer, causing enormous tides in the early oceans. The day was shorter, perhaps only 18 hours long, because the Earth was spinning faster. The atmosphere contained methane, ammonia, and almost no oxygen. Ultraviolet radiation from the sun, unfiltered by an ozone layer, bathed the surface in deadly rays. Life, if it existed, was simple and confined to protected environments. Over the billions of years since, these mountains have endured transformations that strain our imagination. They have been buried under kilometers of sediment, only to be exposed again by erosion. They have been heated and squeezed by tectonic forces, their minerals recrystallizing. They have been subjected to impacts from asteroids, to volcanic eruptions that covered vast areas in lava, to ice ages that buried them under glaciers kilometers thick. Through all of this, the rocks have persisted, changed but intact. The weathering of ancient mountains is a slow but inexorable process. Chemical weathering occurs when rainwater, slightly acidic from dissolved carbon dioxide, reacts with minerals in the rock, breaking them down into clays and dissolved ions. This process is accelerated by plants, whose roots pry into cracks and whose acids further break down minerals. Physical weathering happens through the expansion and contraction of rock due to temperature changes, through the freezing of water in cracks, and through the abrasion of wind and water. In cold climates, frost wedging is a powerful agent of weathering. Water seeps into cracks in the rock. When it freezes, it expands by about 9%, exerting enormous pressure on the surrounding rock. Over many freeze-thaw cycles, the crack widens until eventually a piece of rock breaks off. This process creates the talus slopes you see at the base of many mountain cliffs, piles of angular rock fragments that have fallen from above. In hot climates, thermal expansion and contraction can cause rock surfaces to spool or flake off. The outer surface of a rock heats up during the day and expands. At night it cools and contracts. Over time, this cycling can cause the surface to crack and peel away, like layers of an onion. Desert rocks often show this type of weathering, with curved shells of rock lying at the base of larger boulders. The rate of weathering varies depending on climate, rock type, and exposure. In humid tropical climates, weathering is rapid. Thick soils form and bedrock is deeply weathered. In cold, dry climates, weathering is much slower. In some Antarctic valleys, rocks sit on the surface with minimal weathering for millions of years, preserved by the cold, dry conditions. The age of mountains, then, is not just a matter of when they were uplifted, but also of how long they have been exposed to, the elements, and how rapidly those elements have worn them down. Ancient mountains also teach us about the impermanence of all things. The Appalachians have been mountains, then nearly plains, then mountains again. The forces that raised them have long since ceased, but the mountains remain, testament to the time required for erosion to do its work. Even the hardest granite weathers away, given enough time. Even the highest peaks are eventually reduced to hills, then to gentle rises, and finally to flatland indistinguishable from any other part of the continental surface. But the atoms that made up those mountains do not disappear. They are carried away by rivers and deposited in the ocean. There, they may form new sedimentary rocks, which may one day be uplifted into new mountains. The rock cycle, a continuous process of creation, destruction, and recreation, ensures that nothing is truly lost. The minerals that once stood at the peak of an ancient mountain range may now lie at the bottom of the ocean, waiting to be lifted again by future tectonic movements. In this way, mountains are recycled, their substance enduring even as their forms change. The very existence of such ancient mountains fills some people with a sense of perspective, even peace. In a world that often feels chaotic and uncertain, where change happens faster than we can process it, mountains offer a different timescale. They remind us that some things are measured not in days or years, but in millions and billions of years. They remind us that we are part of a much larger story, a story that began long before us and will continue long after. And perhaps there is comfort in that, in knowing that the world is old, resilient, and patient beyond measure. The existence of such ancient mountains also tells us something hopeful. Despite all the changes Earth has undergone, despite volcanic eruptions, asteroid impacts, ice ages, and mass extinctions the planet endures, mountains rise, but mountains also stand. They weather the storms of time, and in their persistence there is a kind of reassurance. The Earth has seen far worse than anything happening today, and it has carried on, changed, but unbroken. As you rest tonight, imagine standing at the base of the Barberton Mountains, running your hand over rocks that are 3.6 billion years old. Imagine the patience of stone, the slow wearing away of peaks, the inexorable grinding down of mountains into hills and hills into plains. Imagine the depth of time these mountains have witnessed, and let that vastness put your own worries into perspective. In the lifespan of a mountain, human troubles are fleeting as a breath of wind. Mountains create their own weather in ways that seem almost magical. As you climb higher up a mountainside, the world transforms around you. The air grows colder, the pressure drops, the wind picks up. Weather that was calm at the base can be violent at the peak. Within just a few kilometers of vertical distance, you can pass through climate zones that would normally be separated by thousands of kilometers of latitude. Mountains compress the world's climates into vertical bands, stacking ecosystems on top of one another like layers in a cake. The most obvious change as you ascend a mountain is the drop in temperature. On average, the air temperature decreases by about 6 degrees Celsius for every 1,000 meters of elevation gained. This is called the lapse rate, and it occurs because air pressure decreases with altitude, and lower pressure means lower temperature. When air rises, it expands because there is less pressure pushing on it from above. As it expands, it uses energy, and that energy comes from its own heat, so the air cools. This relationship between altitude and temperature is remarkably consistent. Climb a 1,000-meter mountain in the tropics, and the summit will be about 6 degrees cooler than the base. Climb a 1,000-meter mountain in the temperate zone, and the temperature drop will be similar. This is why even tropical mountains can have snow on their peaks. Mount Kilimanjaro in Tanzania sits just a few degrees south of the equator, but its summit at nearly 5,900 meters is cold enough to maintain glaciers. The temperature at the base might be 25 degrees Celsius, but at the summit it averages around -7 degrees. Moving up 100 meters on a mountain is roughly equivalent to moving 80 kilometers toward the nearest pole in terms of climate. This means that climbing a tall mountain in the tropics can be like traveling from the equator toward the Arctic or Antarctic. You begin in hot, humid conditions, perhaps in a rainforest. As you climb, the forest changes, becoming cooler and mistier. Eventually you emerge above the tree line into alpine meadows and tundra. Higher still, you enter a realm of bare rock, ice and snow, conditions similar to the polar regions. All of this within a few hours of vertical climbing. The atmospheric pressure also decreases with altitude. At sea level, the atmosphere presses down with a weight of about 1,000 hectopascals, or 14.7 pounds per square inch. At 3,000 meters, the pressure has dropped to about 700 hectopascals. At 5,500 meters, near the top of Mount Kilimanjaro, it's down to 500 hectopascals, half of sea level pressure. This has profound effects. There is less oxygen available in each breath. The boiling point of water drops, so water boils at 80 degrees Celsius instead of 100 at high elevations, making it harder to cook food. The thin air provides less insulation, so temperatures can swing wildly between day and night. Mountains also force air to move upward, and this creates precipitation. When moist air encounters a mountain range, it has nowhere to go but up. As it rises, it cools, and cool air can hold less moisture than warm air. The water vapor condenses into clouds and eventually falls as rain or snow. This is called orographic precipitation, and it is why the windward side of a mountain range, the side facing the prevailing winds, is often lush and wet, while the leeward side, the side sheltered from the wind, is dry. The phenomenon is striking in places like the Pacific Northwest of North America. Moist air from the Pacific Ocean blows eastward until it hits the Cascade Range. Forced to rise, the air cools and dumps enormous amounts of rain and snow on the western slopes. Places like the Hoh Rainforest in Washington state receive over 3,600 millimeters of rain per year, making it one of the wettest places in the contiguous United States. But just 100 kilometers to the east, on the far side of the Cascades, the land is semi-arid, receiving less than 250 millimeters of rain per year. The mountains have wrung nearly all the moisture from the air, creating what is called a rain shadow. This pattern repeats around the world. The Himalayas block the summer monsoons from reaching the Tibetan Plateau, making Tibet one of the driest regions in Asia, despite being surrounded by some of the wettest. The Andes create a rain shadow over Patagonia, and the southern Alps of New Zealand divide the South Island into a wet, forested west and a drier, grassy east. Mountains also generate their own winds. During the day, the sun heats the slopes and the warm air rises, creating an upslope breeze called an anabatic wind. At night, the slopes cool faster than the valley air, and the cool, dense air drains downward, creating a downslope breeze called a katabatic wind. These mountain and valley winds create a daily breathing cycle, with air flowing uphill during the day and downhill at night. Then there are the foehn winds, warm, dry winds that descend the leeward side of a mountain range. As air descends, it compresses and heats up, often becoming much warmer than it was before it started climbing the mountain. Foehn winds can raise temperatures dramatically in just a few hours. In the Alps, these winds can melt snow in the middle of winter, earning them the nickname snow eater. They can also create dangerous fire conditions in places like California, where descending winds from the mountains can turn dry vegetation into a tinderbox. High mountains also experience extreme weather. The summit of Mount Washington in New Hampshire, though only 1,900 meters high, holds the record for the highest wind speed ever recorded on Earth's surface at 372 kilometers per hour. The mountain sits at the intersection of several storm tracks, and its summit protrudes into the jet stream, the fast-moving river of air high in the atmosphere. Conditions on Mount Washington can change from calm to life-threatening in minutes, with hurricane-force winds, blinding snow, and temperatures that drop to minus 40 degrees Celsius. The high peaks of the Himalayas endure even worse. Above 8,000 meters, climbers enter what is called the death zone, where the air pressure is so low that the human body cannot acclimatize. There is not enough oxygen to sustain life for long. Cold is extreme, with temperatures regularly dropping below minus 40. Winds can exceed 160 kilometers per hour. Frostbite can occur in minutes, and even small mistakes can be fatal. The weather at these altitudes is not just harsh, it is at the very edge of what humans can survive. Mountains also experience temperature inversions, where the normal pattern is reversed and cold air lies beneath warm air. This happens often in mountain valleys. At night, cold air drains down the slopes and pools in the valley bottom, while warmer air remains higher up. If you climb out of a cold, foggy valley in the morning, you might suddenly emerge into warm sunshine just a few hundred meters higher. The inversion can trap fog, pollution, and cold air in the valley for days or even weeks. Cloud forests represent another unique mountain climate. Found in tropical and subtropical mountains, usually between 1,000 and 2,500 meters elevation, cloud forests exist where moisture-laden air from lower elevations rises, cools, and condenses into persistent clouds that envelop the forest. The trees and plants in cloud forests are draped in mosses and epiphytes that capture water directly from the mist. These forests don't rely on rainfall alone. They harvest moisture from the air itself. They are among the most biologically diverse and endangered ecosystems on Earth, found in places like the Andes, the mountains of Central America, and the highlands of Ethiopia. The tree line, the elevation above which trees cannot grow, is determined largely by temperature. Trees need a certain minimum temperature during the growing season to produce enough photosynthesis to survive. In general, the tree line corresponds to where the average temperature of the warmest month is about 10 degrees Celsius. Below this temperature, the growing season is too short or too cold for trees to complete their life cycles. But the exact elevation of the tree line varies depending on latitude, local climate, exposure to wind, and other factors. At the equator, the tree line can be as high as 4,500 meters. In the Alps, it sits around 2,000 to 2,500 meters. In Scandinavia, it drops to about 600 meters, and in the Arctic, trees disappear entirely at sea level. The tree line is one of the most visible boundaries on any mountain, marking the transition from forest to alpine tundra. Above the tree line, low shrubs, grasses, and herbaceous plants dominate, adapted to cold, wind, and a short growing season. Mountain climates also exhibit strong variations over short distances. Slope aspect, whether a slope faces north or south, east or west, makes an enormous difference. In the northern hemisphere, south-facing slopes receive more direct sunlight and are warmer and drier. North-facing slopes are cooler and moister, often retaining snow longer into spring. In steep mountain terrain, north and south slopes can support entirely different vegetation communities, with the south slope hosting dry, open forests or grasslands, while the north slope hosts dense, shady forest. Mountains are more sensitive to climate change than lowlands. Over the past century, mountains have warmed at nearly twice the rate of the global average. This enhanced warming, called elevation-dependent warming, happens for several reasons. As snow and ice melt, they expose darker rock and soil, which absorbs more sunlight and accelerates warming. Glaciers reflect sunlight, but bare ground absorbs it. As glaciers disappear, mountains warm faster. The climate zones on mountains are shifting upward. Tree lines are moving higher. Alpine plants, already at the limits of where they can survive, are being pushed toward the summits, with nowhere left to go. In the European Alps, the average temperature at 1,500 meters has increased by about 1.5 degrees Celsius over the past century, compared to 1 degree Celsius in the lowlands. This doesn't sound like much, but for ecosystems adapted to narrow temperature ranges, it can mean the difference between survival and extinction. As you rest tonight, imagine standing on a mountainside at dawn. Below you, the valley is still wrapped in darkness and cold. But you are above it, already in sunlight, the air warming around you. You climb higher, passing through layers of climate, from warm to cool to cold. The air grows thinner, your breath becomes visible, the wind picks up. Finally, you reach a place where no trees grow, where only the toughest plants cling to cracks in the rock. The summit is not far now, but the weather has turned harsh, clouds swirling around you, snow beginning to fall even though it's summer. You turn back, descending through the layers again, and with each step downward, the world softens, warms, and welcomes you home. Mountains are nature's vertical laboratories, compressing into a few thousand meters of elevation, what would normally take thousands of kilometers of latitude to experience. As you climb a mountain, you pass through distinct bands of life, each adapted to the specific conditions of temperature, moisture, and exposure found at that elevation. These are called life zones or altitudinal zones, and they transform mountains into islands of biodiversity, harboring species found nowhere else on Earth. The journey begins at the base, where the mountain meets the surrounding lowlands. In the tropics, this might be a dense rainforest, hot and humid, filled with the sounds of insects and birds. In temperate regions, it could be a mixed deciduous forest of oak, maple, and hickory, or perhaps a grassland or desert depending on the local climate. Whatever the starting ecosystem, it changes as you climb. In tropical mountains, the lower slopes are often covered in montane rainforest, a lusher, mistier version of lowland rainforest. This forest grows in the zone where warm, moist air rises and condenses into persistent clouds. The trees are shorter than in lowland forests, and their branches are draped with epiphytes, plants that grow on other plants. Mosses, ferns, orchids, and bromeliads cover every available surface, creating a living carpet of green. These forests are incredibly biodiverse. In the Andes, a single hectare of montane forest can contain hundreds of tree species. As you continue climbing, you enter the cloud forest zone, where conditions are perpetually cool and misty. The clouds that form here are not high in the sky, but low enough to engulf the forest itself. The trees become stunted and gnarled, twisted by constant wind and moisture. Visibility drops to just a few meters. Everything is wet, dripping, covered in moss. Walking through a cloud forest feels like moving through a dream, soft and silent except for the occasional call of a bird or the drip of water from the leaves. Cloud forests are among the most threatened ecosystems on Earth. They occupy a narrow elevation band, and climate change is causing this band to shift upward, shrinking the habitat available. Many species that live in cloud forests are endemic, found only in a specific mountain range or even a specific peak. If their habitat disappears, they have nowhere to go. Higher still, you reach the montane forest zone, where conifers often dominate in temperate and boreal regions. Spruces, firs and pines are adapted to the cooler temperatures and shorter growing seasons found at these elevations. The forest is quieter here, less dense, with fewer understory plants. The air smells of pine resin. The light filters through the canopy in soft beams. Snow can fall even in summer, and the ground may be covered with pine needles and moss. At the upper edge of the forest, trees become increasingly sparse and stunted. This is the Krummholz zone, a German word meaning crooked wood. Here, at the limit of where trees can grow, they are battered by wind and cold. Instead of growing tall, they grow horizontally, their branches bent and twisted, their trunks barely above head height. In winter, heavy snow bends them further, and only the branches protected beneath the snowpack survive. Trees in the Krummholz zone can be centuries old but only a few meters tall, their growth rings so tightly packed that you can barely count them. Finally, you cross the tree line and the forest ends. Above the tree line lies the Alpine zone, a realm of tundra, meadows and bare rock. No trees grow here, only low shrubs, grasses and herbaceous plants. The growing season is short, sometimes just a few weeks. Winters are long and harsh, yet alpine ecosystems burst with life during the brief summer. Meadows explode with wildflowers, their colours brilliant against the snow and rock. Marmots whistle from boulder piles. Pikas gather grasses for their winter stores. Birds nest on the ground, and insects swarm in the thin air. Alpine plants are marvels of adaptation. Many form cushions, compact mounds that trap heat and reduce water loss. Some have hairy leaves to insulate against cold and wind. Others produce dark pigments to absorb as much sunlight as possible. Alpine flowers are often disproportionately large for the size of the plant, because they need to attract pollinators quickly during the short window when conditions allow. Some plants can photosynthesize at temperatures near freezing, and some can survive being frozen solid, their cells protected by special proteins that prevent ice crystals from forming. Even higher, above about 5,000 meters in the tropics, or 3,000 meters in temperate zones, lies the Nevel zone, the realm of permanent snow and ice. Life does not end here, but it becomes sparse and specialized. Certain lichens and mosses can grow on rock surfaces, and some insects and spiders live in crevices, feeding on wind-blown organic matter. Even at the summit of Mount Everest at 8,849 meters, jumping spiders have been found, the highest known permanent residents on Earth. Mountains harbor an astonishing proportion of Earth's biodiversity. Though they cover only about 25% of the land surface, mountains are home to more than 85% of the world's amphibians, birds and mammals. Many of these species are endemic, found only in mountains. This is partly because mountains create isolated habitats. A species living on one peak may be separated from relatives on another peak by inhospitable lowlands, just as effectively as if separated by an ocean. Over time, these isolated populations evolve into distinct species. The high biodiversity of mountains also results from the variety of habitats they provide. In just a few kilometers of elevation, you pass through multiple climate zones, each with its own suite of species. A mountain range can contain tropical forests, temperate forests, and Arctic tundra, all in close proximity. This diversity of habitats supports a diversity of life. Some mountains are biodiversity hotspots of global significance. The mountains of New Guinea host over 20,000 plant species, about 10% of the world's total, in an area smaller than Texas. The tropical Andes are home to about 1/6 of all plant species on Earth. The Caucasus Mountains in Asia contain a remarkable diversity of species found nowhere else. The mountains of the Mediterranean region, the mountains of East Africa, and the mountains of southwestern China are all recognized as centers of exceptional biodiversity. Mountains also serve as refuges for species during periods of climate change. During ice ages, when ice sheets covered much of the northern continents, some species retreated into mountain ranges where microclimates and varied topography provided sheltered areas that remained ice-free. The Appalachian Mountains served this role in North America. As glaciers advanced from the north, many northern species found refuge in the cooler elevations of the southern Appalachians. When the ice retreated, these species remained, creating pockets of northern flora and fauna far south of where they are typically found. Today, you can find plants and animals in the Great Smoky Mountains that are more typical of Canada. Mountains also influence the evolution of species. The isolation of mountain habitats promotes speciation, the formation of new species. The varied terrain creates countless ecological niches. The steep environmental gradients from base to peak select for different traits at different elevations. Over time, populations become adapted to their specific elevation, and gene flow between elevations decreases. Eventually, they may become distinct species. Animals in mountain ecosystems face unique challenges. They must cope with low oxygen, cold temperatures, high UV radiation, and steep terrain. Mountain goats and sheep are adapted to life on cliffs, with hooves designed to grip narrow ledges and powerful legs for jumping across gaps. Many mountain mammals grow thick fur and put on fat to survive the winter. Birds that live at high elevations often have larger hearts and lungs to extract oxygen from the thin air. Even insects show adaptations, such as darker coloration to absorb heat and reduce activity levels to conserve energy. Migration is common in mountain ecosystems. Many animals move up and down the mountain seasonally, following the availability of food. Elk and deer descend from the high country in winter, seeking lower elevations where snow is less deep and forage is more accessible. Birds may nest at high elevations in summer, but migrate to the valleys, or even to lower latitudes in winter. Some species, like pikas, remain active year-round, living under the snowpack in winter, moving through tunnels and feeding on grasses they harvested during summer. The soils in mountain ecosystems vary widely. At lower elevations, where temperatures are warmer and biological activity is high, soils can be rich and deep, supporting dense forests. At higher elevations, soils are thinner, colder, and poorer in nutrients. Above the tree line, soil development is slow, and in many places, vegetation grows directly on broken rock with little soil at all. Erosion is a constant challenge. On steep slopes, soil can wash away easily, and landslides are common. Water is abundant in mountains, flowing down from snowmelt, glaciers, and rainfall. Mountain streams are cold, clear, and fast-moving, tumbling over rocks in waterfalls and rapids. These streams support unique aquatic ecosystems adapted to high oxygen levels, cold temperatures, and strong currents. Fish in mountain streams, like trout and salmon, are often adapted to swim against powerful flows and to survive in icy water. Alpine lakes, often formed in basins carved by ancient glaciers, are another distinctive feature of mountain ecosystems. These lakes are typically oligotrophic, meaning they are clear and low in nutrients. They freeze solid in winter and are ice-free for only a few months each year. Despite these harsh conditions, they host life, including zooplankton, insect larvae, and in some cases, fish. The beauty of mountain ecosystems is matched by their fragility. Because conditions are so specific at each elevation, even small changes in climate can have large impacts. As temperatures rise, the climate zones shift upward, and species must move to stay within their preferred temperature range. But there is a limit to how far up they can go. Species already living at the summit have nowhere left to retreat. They risk extinction as their habitat disappears. Mountain ecosystems also demonstrate remarkable examples of convergent evolution, where unrelated species in different parts of the world evolve similar adaptations to similar challenges. Alpine plants on different continents often look similar, with cushioned growth forms, small leaves, and bright flowers, even though they may belong to completely different plant families. Similarly, mountain animals like mountain goats in North America and ibex in Europe have evolved similar adaptations for life on cliffs, even though they are not closely related. The soil organisms in mountain ecosystems, though less visible than plants and animals, play crucial roles. Fungi form mycorrhizal associations with plant roots, helping plants absorb nutrients from the poor alpine soils, in exchange for sugars from photosynthesis. These fungal networks connect plants underground, allowing them to share resources and information. In some cases, these networks are so extensive that they link entire plant communities, creating a kind of underground internet of roots and fungi. Decomposition in mountain ecosystems is slow, especially at high elevations where cold temperatures limit microbial activity. Organic matter can accumulate, with dead plants taking years or even decades to fully decompose. This creates a kind of carbon storage, with mountain soils holding significant amounts of organic carbon. In permafrost regions, organic matter can be frozen for thousands of years, effectively removing it from the carbon cycle until the permafrost thaws. The insects of mountain ecosystems are often overlooked, but they are essential. Bees, flies, and beetles pollinate alpine flowers. Ants and beetles break down organic matter. Butterflies add splashes of colour to mountain meadows. Some insects, like the Himalayan jumping spider found near the summit of Everest, have adapted to survive at extreme altitudes where most life cannot exist. These spiders feed on springtails and other tiny arthropods that are blown up the mountain by wind, an entire ecosystem based on wind-delivered food. Birds are conspicuous members of mountain communities. Some, like the alpine chough, live year-round at high elevations, even in winter. These birds have adaptations like increased blood oxygen capacity and efficient metabolism that allow them to function in thin air. Others, like hummingbirds, visit mountains only during the summer breeding season. In the Andes, some hummingbirds feed at elevations above 4,000 meters, hovering in the thin air to sip nectar from alpine flowers. Large mammals in mountains face particular challenges. They must find enough food to sustain their large bodies in environments where productivity is low. Mountain sheep and goats are grazers and browsers, feeding on grasses, forbs, and shrubs. They move seasonally, following the availability of food. In winter, they descend to lower elevations or congregate in areas where wind blows the snow away, exposing vegetation. In summer, they climb to high alpine meadows where food is abundant. Predators in mountain ecosystems must also adapt. Wolves, mountain lions, bears, and lynx hunt the herbivores that live in mountains. These predators often have large home ranges because prey is scattered and seasonal. They may follow prey up and down the mountain as seasons change, or they may use valleys as travel corridors between different areas. The balance between predators and prey helps maintain healthy populations and prevents overgrazing of fragile alpine vegetation. Aquatic ecosystems in mountains are unique and often overlooked. Mountain streams, with their cold, oxygen-rich water and strong currents, support specialized communities. Fish like trout and salmon are adapted to these conditions, with streamlined bodies for swimming in fast current and the ability to thrive in cold water. Aquatic insects, including mayflies, stoneflies, and caddisflies, spend most of their lives as larvae in the stream, adapted to cling to rocks in the current. These insects are indicators of water quality. Their presence tells us the stream is healthy. Alpine lakes formed in glacial basins are often oligotrophic, meaning they are low in nutrients. Their water is clear and cold, sometimes barely above freezing even in summer. Despite these harsh conditions, they support life. Zooplankton, tiny animals that drift in the water, form the base of the food web. Small fish, when present, feed on zooplankton and insects. Some alpine lakes have no fish at all, either because they are too isolated or because the conditions are too extreme. In these fishless lakes, aquatic insects and amphibians like salamanders may be the top predators. The interconnectedness of mountain ecosystems means that changes at one elevation can affect life at other elevations. A forest in the montane zone may depend on pollinators that overwinter in the lowlands. A predator in the alpine may hunt prey that spend part of the year in the forest below. Water flowing down from alpine snowmelt nourishes ecosystems at all elevations. Understanding these connections is essential for conservation, because protecting one part of the mountain is not enough. The entire gradient from base to summit needs to be considered as a single integrated system. As you drift off tonight, imagine walking through a mountain forest. You start in the cool shade of the montane zone, surrounded by towering conifers. The forest floor is soft with moss and pine needles. As you climb, the trees become smaller, more twisted. You enter the krummholz where trees crouch low, shaped by wind. Then, suddenly, you step out of the forest into the open alpine zone. Meadows of wildflowers stretch before you, swaying in the breeze. The air is thin and cool. Above, peaks rise into the sky, bare rock and snow. Somewhere a marmot whistles. Somewhere a ptarmigan calls. You're in the Alpine, a place of beauty and harshness, of life clinging to the edge of what is possible. The world's great mountain ranges are not just geological features, but also characters in humanity's story. They have shaped civilizations, inspired myths, challenged explorers, and guarded secrets for millennia. Each range has its own personality, its own story written in stone and ice, and each holds lessons about the power and patience of the earth. The Himalayas are the youngest and highest mountain range on Earth, a chain of peaks that includes all 14 of the world's 8,000-metre mountains. The name, Himalaya, comes from Sanskrit meaning abode of snow, and it is fitting. The range stretches about 2,400 kilometres across 5 countries: India, Nepal, Bhutan, China and Pakistan. The Himalayas began forming about 50 million years ago and are still rising today, gaining about 5 millimetres of height each year. The highest peak in the Himalayas and the world is Mount Everest, known as Sagarmatha in Nepali and Chomolungma in Tibetan. At 8,049 metres above sea level, Everest's summit sits in the jet stream, a fast-moving river of air high in the atmosphere. Winds on the summit can exceed 250 km per hour, and temperatures drop below -40 degrees Celsius. The summit is so high that there is only about 1/3 the oxygen available at sea level, yet thousands of people have climbed it, drawn by the challenge and the glory of standing on the top of the world. The Himalayas are not just tall, they are also massive. They contain the largest volume of ice outside the polar regions, earning them the nickname the Third Pole. Thousands of glaciers cover the high peaks, feeding major rivers like the Ganges, Indus and Brahmaputra. More than 1 billion people depend on water from these mountains, making the Himalayas one of the most important water sources on Earth. But the glaciers are melting rapidly due to climate change, threatening this water supply. The Himalayas also create a massive climate barrier. They block cold, dry air from the Tibetan Plateau from moving south and prevent the warm, moist monsoon air from moving north. This is why India and Bangladesh receive heavy monsoon rains, while Tibet remains one of the driest regions in Asia. The Himalayas essentially split Asia into 2 distinct climate zones. The Andes, the longest continental mountain range on Earth, stretch more than 7,000 kilometers along the western edge of South America, passing through 7 countries from Venezuela to Chile. The Andes are a volcanic arc formed by the subduction of the Nazca Plate beneath the South American plate. The range includes numerous active volcanoes, some of the world's highest, and experiences frequent earthquakes. The Andes are incredibly diverse. In the north, near the equator, they are wet and tropical. In the central Andes, they are arid, home to high-altitude deserts and salt flats like the Uyuni Salt Flat in Bolivia, the largest salt flat on Earth. In the south, in Patagonia, they are cool and glaciated, with fjords and temperate rainforests. The variation in climate and altitude creates an extraordinary range of ecosystems and species. The Andes were home to the Inca Empire, one of the largest and most sophisticated civilizations of pre-Columbian America. The Inca built cities high in the mountains, including Machu Picchu, the iconic ruins perched on a ridge at 2,430 meters. They developed agricultural techniques suited to steep slopes, such as terracing and irrigation, and they domesticated crops like potatoes and quinoa that are now grown worldwide. The mountains were central to Inca religion and culture, with many peaks considered sacred. Today, millions of people live in the Andes, many in cities built at altitudes that would be considered extreme in other parts of the world. La Paz, Bolivia, at 3,650 meters, is the world's highest capital city. Residents of the Andes have adapted to high altitude over generations, with larger lung capacity and more efficient oxygen transport in their blood compared to lowland populations. The Alps, though smaller and older than the Himalayas or Andes, are perhaps the most studied mountain range in the world. They stretch about 2,200 kilometers across 8 countries in Central Europe. The Alps were formed by the collision of the African and Eurasian plates, beginning about 65 million years ago. The highest peak, Mont Blanc, rises to 4,808 meters. The Alps have played a central role in European history. They formed a natural barrier between northern and southern Europe, influencing the movement of people, armies, and cultures. Yet they also contained passes that allowed trade and travel, such as the Brenner Pass and the St. Gothard Pass. Hannibal famously crossed the Alps with elephants during the Second Punic War, and Napoleon led armies through alpine passes. The Alps are also the birthplace of modern mountaineering. In the 18th and 19th centuries, climbers began to ascend alpine peaks as a sport, and the Alps became a playground for adventurers. The first ascent of the Matterhorn in 1865 was a landmark event, though it ended in tragedy when 4 of the 7 climbers died during the descent. Today, the Alps attract millions of visitors each year for hiking, skiing and climbing. The Rockies, or Rocky Mountains, are a major mountain range in western North America, stretching more than 4,800 kilometers from New Mexico to British Columbia. They're relatively young, having formed between 80 and 55 million years ago during a period of mountain building called the Laramide Orogeny. Unlike typical subduction-related mountain building, the Rockies formed farther inland, possibly due to the shallow angle of the subducting plate beneath North America. The Rockies are diverse, containing a mix of sedimentary, volcanic and metamorphic rocks. They are home to iconic national parks like Yellowstone, Rocky Mountain and Glacier, each showcasing different aspects of mountain geology and ecology. Yellowstone sits atop a volcanic hotspot with geysers and hot springs that reveal the heat beneath the surface. Glacier National Park, on the border of Montana and Alberta, contains some of the most spectacular alpine scenery in North America, though its namesake glaciers are rapidly disappearing due to climate change. The Rockies were a major barrier to westward expansion in North America during the 19th century. Crossing them required finding passes through the mountains, and the discovery of routes like South Pass in Wyoming opened the way for wagon trains heading to Oregon and California. The Rockies were also the site of major gold and silver discoveries, leading to mining booms that shaped the development of the American West. The Caucasus Mountains, lying between the Black Sea and the Caspian Sea, form the traditional boundary between Europe and Asia. They stretch about 1,200 kilometers through Russia, Georgia, Armenia and Azerbaijan. Mount Elbrus at 5,642 meters is the highest peak in the Caucasus and the highest in Europe. The Caucasus are geologically young, formed by the collision of the Arabian and Eurasian plates. The Caucasus are known for their cultural and linguistic diversity. More than 50 ethnic groups live in the region, speaking languages from several different language families. The mountains have served as a refuge for cultures and languages that have disappeared elsewhere, preserving traditions that date back thousands of years. The region is also known for its biodiversity, with many endemic species. The Atlas Mountains of North Africa extend about 2,500 kilometers through Morocco, Algeria and Tunisia. They were formed by the collision of the African and Eurasian plates, the same collision that created the Alps. The Atlas Mountains are not as high as other famous ranges, with the highest peak, Toubkal, reaching 4,067 meters, but they play a crucial role in the climate of North Africa. The Atlas Mountains capture moisture from the Atlantic, creating a wetter climate on their northern and western slopes, while the Sahara Desert lies to the south and east. The mountains support forests of cedar, oak and pine, a striking contrast to the surrounding arid landscapes. The Berber people have lived in the Atlas Mountains for thousands of years, developing a culture adapted to the mountainous terrain. Each of these mountain ranges tells a unique story, but all share common themes. They are places of extremes, of beauty and danger, of life and barrenness. They are barriers and bridges, dividing lands and peoples, but also connecting them through passes and trade routes. They are sources of water, minerals and inspiration. They challenge us, humble us, and remind us of the forces that shape our planet. As you rest tonight, imagine standing before these ranges, feeling small beneath their immensity. Picture the Himalayas, their summits disappearing into the clouds, snow streaming from their peaks in the jet stream winds. See the Andes, a spine of volcanoes and ice running the length of a continent. Feel the presence of the Alps, ancient yet still young compared to the mountains of the east. These ranges have stood for millions of years, and they will stand for millions more long after all of us are gone. Mountains have always held a special place in human consciousness. They appear in myths and religions as homes of gods, as sacred sites, as places of revelation and transformation. They have been obstacles to overcome and refuges to retreat to. They have provided resources and challenged survival. The relationship between humans and mountains is one of reverence, fear, exploitation, and dependence. Many cultures have viewed mountains as sacred. In ancient Greek mythology, Mount Olympus was the home of the gods. In Japanese culture, Mount Fuji is a sacred peak climbed by pilgrims seeking spiritual purification. In Hindu and Buddhist traditions, Mount Kailash in Tibet is believed to be the abode of Lord Shiva and a site of immense spiritual power. No one has climbed Kailash, not because it is too difficult, but because it is too sacred. The mountain is off-limits to climbers, protected by the reverence of millions. Mountains appear in the Bible and other religious texts as places where humans encounter the divine. Moses received the 10 Commandments on Mount Sinai. Muhammad received the first revelation of the Quran in a cave on Mount Hira. The Sermon on the Mount, one of Jesus' most famous teachings, takes place on a mountainside. Mountains, being high and difficult to reach, are seen as closer to heaven, as thresholds between the earthly and the divine. For many indigenous peoples, mountains are not just sacred, they are alive, beings with their own agency and consciousness. The Maori of New Zealand view mountains like Taranaki and Ruapehu as ancestors. The Quechua people of the Andes make offerings to the Apus, the mountain spirits. The Sherpa people of the Himalayas honour the mountains as gods, and before climbing they perform ceremonies to ask permission and seek protection. Mountains have also been barriers. They divide regions and cultures, making travel difficult and isolating communities. The Alps divided northern and southern Europe for centuries. The Himalayas separated the Indian subcontinent from Central Asia. The Andes divided the Pacific coast of South America from the interior. These barriers shaped the development of distinct cultures and languages, as communities on opposite sides of a range had little contact with each other. Yet mountains also contain passes, routes through the heights that allow trade and travel. The Silk Road crossed the Pamir and Tian Shan mountains, connecting China with the Middle East and Europe. The Inca built roads through the Andes, including suspension bridges over deep gorges. The Roman Empire maintained roads through Alpine passes to move armies and goods between Italy and the provinces to the north. Humans have lived in mountains for thousands of years, developing cultures and economies adapted to high altitudes and steep terrain. Mountain people often practice agriculture on terraced slopes, carving steps into the hillsides to create flat land for crops. In the Andes, the Inca perfected this technique, building terraces that are still in use today. In the Himalayas, rice paddies cling to impossibly steep slopes, fed by intricate irrigation systems. Mountain communities have also herded animals, taking advantage of high-altitude pastures in summer. Transhumance, the seasonal movement of livestock between lowland and highland pastures, has been practiced for millennia in places like the Alps, the Pyrenees, and the mountains of Central Asia. Sheep, goats, and yaks are well suited to mountain life, able to thrive on sparse vegetation and navigate steep terrain. Mountains provide essential resources. Timber from mountain forests has been harvested for construction and fuel for centuries. Mountain rivers, fed by snowmelt and glaciers, provide water for drinking, irrigation, and hydropower. Mountains are rich in minerals, with gold, silver, copper, and other metals often found in mountain rocks. Many of the world's great mining regions are in mountains, from the silver mines of the Andes to the gold fields of the Sierra Nevada. But the exploitation of mountain resources comes at a cost. Deforestation on mountain slopes leads to erosion and landslides. Mining scars the landscape and pollutes rivers. The construction of dams and roads fragments habitats and disrupts ecosystems. Sustainable management of mountain resources is a growing challenge as populations increase and demand for resources intensifies. Tourism has become a major industry in many mountain regions. Millions of people visit mountains each year to hike, climb, ski, and experience the natural beauty. This brings economic benefits to mountain communities, but also creates problems. Popular peaks like Everest have become crowded, with long lines of climbers waiting to reach the summit. Trails erode under heavy foot traffic. Waste, including human waste, accumulates at high-altitude camps. The challenge is to balance the economic benefits of tourism with the need to protect fragile mountain environments. Climate change is altering the relationship between humans and mountains. Glaciers that have provided reliable water supplies for centuries are shrinking or disappearing. Ski resorts at lower elevations are struggling, as winters become warmer and snowfall less reliable. Alpine meadows used for grazing are drying out. Communities that depend on meltwater are facing an uncertain future, as the glaciers that feed their rivers waste away. Mountains have also inspired art, literature, and science. Romantic poets like Wordsworth and Shelley found inspiration in the Alps. Painters like Albert Bierstadt captured the majesty of the American Rockies. Mountaineers have written accounts of their climbs that read like epics, tales of endurance, triumph, and tragedy. The first ascent of Annapurna in 1950 was documented in Morris Herzog's book, a harrowing story of ambition and survival. Scientists have been drawn to mountains as natural laboratories. Alexander von Humboldt's observations in the Andes in the early 19th century helped establish the field of biogeography. The study of alpine plants has contributed to our understanding of adaptation and evolution. Glaciologists study mountain glaciers to understand climate change. Geologists study mountain rocks to learn about the formation of continents. Mountains are laboratories where theories are tested against the reality of rock and ice. For many people, mountains represent challenge and adventure. Climbing a peak, even a modest one, is an achievement. It requires physical effort, mental determination, and a willingness to face fear. The history of mountaineering is filled with stories of explorers pushing the limits of human endurance, of triumphs and tragedies. The first ascent of Everest by Edmund Hillary and Tenzing Norgay in 1953 was celebrated around the world, a symbol of human achievement. Yet mountains have also claimed many lives. K2, the world's second highest peak, has a fatality rate of about 1 death for every 4 successful summits, earning it the name Savage Mountain. Mountains teach humility. No matter how skilled or prepared a climber is, the mountains are indifferent. Weather can change in minutes. Avalanches can strike without warning. Altitude sickness can incapacitate even the fittest climber. Mountains remind us that we are small, that nature is powerful, and that some forces are beyond our control. This is a lesson that modern society, with its technology and comfort, sometimes forgets. But mountains do not forget. They remain wild, untamed, and ultimately unknowable. As you lie here tonight, think about the mountains nearest to you. Perhaps you've seen them on the horizon, or perhaps you've stood on one looking out over the world below. Think about the people who have lived in those mountains, who have climbed them, who have drawn life from them. Mountains are more than rock and ice. They are part of our story, part of our imagination, part of what makes us human. Mountains are not static lumps of rock. They are dynamic systems, constantly changing, constantly in motion. Water flows through them in rivers and streams. Ice creeps down their slopes and glaciers. Beneath the surface, caves wind through the rock, carved by water over thousands of years. These hidden features shape the landscape, create ecosystems, and reveal the mountain's inner workings. Glaciers are rivers of ice that flow down mountainsides under their own weight. They form in areas where more snow falls in winter than melts in summer, creating a net accumulation of snow over time. The snow compacts into firn, a dense granular ice, and eventually into solid glacial ice. As the ice thickens, it begins to flow, moving downslope at rates that vary from a few meters per year to several hundred meters per year, depending on the slope, the temperature, and the amount of meltwater lubricating the base. Mountain glaciers are found on every continent, from the tropics to the poles. The largest are found in Alaska, the Himalayas, the Andes, and the Alps. Some are small cirque glaciers, occupying bowl-shaped depressions high on a mountainside. Others are valley glaciers, flowing down entire valleys like slow-motion rivers. A few are Piedmont glaciers, which spread out into broad lobes when they reach the lowlands at the base of a mountain range. Glaciers are powerful sculptors of the landscape. As they move, they pluck rocks from the bedrock and carry them downslope. The rocks embedded in the ice act like sandpaper, grinding and polishing the bedrock beneath. This erosion carves deep U-shaped valleys with steep walls and flat floors. When the glacier retreats, it leaves behind these valleys, along with other distinctive landforms. One such landform is a cirque, a bowl-shaped depression carved into a mountainside by a glacier. Cirques form at the head of a glacier, where snow accumulates and erosion is most intense. When the glacier melts, the cirque may fill with water, creating a tarn, a small mountain lake. Cirques often have steep, nearly vertical headwalls, the result of intense erosion by the glacier and frost action on the rock above. Another glacial feature is a moraine, a ridge or pile of rock debris deposited by a glacier. There are several types of moraines. Lateral moraines form along the sides of a glacier, where debris falls onto the ice from the valley walls. Medial moraines form where two glaciers merge, with the lateral moraines of each glacier joining to create a line of debris down the middle of the combined glacier. Terminal moraines form at the end of a glacier, where the ice is melting and dumping its load of rock and sediment. These moraines mark the glacier's maximum extent and can be seen as ridges across a valley long after the glacier has retreated. Glaciers also leave behind erratics, large boulders that the glacier carried far from their source and deposited in places where the rock type is completely different from the local bedrock. Some erratics are the size of houses, perched incongruously on hilltops or in valleys where they clearly don't belong. They are evidence of the glacier's power and reach. Glacial meltwater forms rivers and streams that flow from the glacier's terminus. These rivers are often milky in colour, filled with fine rock flour, sediment ground so finely by the glacier that it remains suspended in the water. The meltwater is cold, just above freezing, and it fluctuates in volume throughout the day and season. In the heat of a summer afternoon, meltwater flows rapidly, swollen by the day's melting. At night, when temperatures drop and melting slows, the flow decreases. In winter, it may stop altogether. Rivers originating from glaciers provide critical water supplies to millions of people. In the Himalayas, glaciers feed the Ganges, Indus, and Brahmaputra rivers, which together support over 1 billion people. In the Andes, glacial meltwater irrigates farmland in regions that receive little rainfall. In the western United States, meltwater from the Sierra Nevada and the Rockies supplies cities and agriculture in arid regions. But glaciers around the world are shrinking. Data from the World Glacier Monitoring Service shows that reference glaciers have lost ice, equivalent to slicing nearly 30 metres off the top of each glacier since 1970. The pace of loss is accelerating. Glaciers that have occupied their valleys for thousands of years are disappearing within decades. Some are already gone, leaving behind empty valleys and a changing landscape. The loss of glaciers has far-reaching consequences. As glaciers shrink, the rivers they feed experience changes in flow. Initially, as the glacier melts faster, the river may carry more water than normal. But once the glacier is gone, or reduced to a fraction of its former size, the river's flow decreases, especially during the dry season when glacier melt would normally supplement flow. This threatens water supplies for drinking, irrigation, and hydropower. Glacial lakes are another feature of mountain landscapes. These lakes form in several ways. Some are dammed by moraines, the ridges of debris left by retreating glaciers. Others form in depressions carved by the glacier. Glacial lakes are often stunningly blue or green, their colour coming from the fine rock flour suspended in the water. The particles scatter light in a way that makes the water appear luminous. Some glacial lakes are dangerous. When a lake is dammed by a moraine or by ice, the dam can be unstable. If the dam fails, the lake can burst out in a catastrophic flood, called a glacial lake outburst flood, or GLOF. These floods can devastate downstream valleys, destroying villages, bridges, and farmland. As glaciers retreat and more lakes form, the risk of GLOFs is increasing in many mountain regions. Caves are another hidden feature of mountains. Most mountain caves form in limestone, a rock that dissolves in slightly acidic water. Rainwater, which absorbs carbon dioxide from the air and soil, becomes a weak acid. As it seeps through cracks in the limestone, it dissolves the rock, slowly widening the cracks into passages and chambers. Over thousands of years, extensive cave systems can develop, with underground rivers, waterfalls, and rooms the size of cathedrals. Carlsbad Caverns in New Mexico and Mammoth Cave in Kentucky are examples of large cave systems in mountainous or hilly regions. These caves contain spectacular formations like stalactites, which hang from the ceiling like icicles, and stalagmites, which build up from the floor. These formations grow as water drips through the cave, depositing dissolved minerals drop by drop over centuries. Some formations are millions of years old. Caves in mountains provide habitat for unique species. Many cave-dwelling animals, called troglobites, are adapted to life in total darkness. They lack eyes and pigmentation, having no need for either in an environment with no light. Bats use caves as roosts, and some caves host enormous colonies numbering in the millions. The Bracken Cave in Texas is home to one of the largest bat colonies in the world, with an estimated 15 million Mexican free-tailed bats emerging each evening in a spectacle that takes hours. Ice caves are a different kind of cave, formed not in rock but in glaciers. Meltwater carves tunnels and passages through the ice, creating labyrinthine networks that shift and change as the glacier moves. Ice caves are dangerous to explore because they can collapse without warning, but they are also stunningly beautiful, with walls of blue and white ice that glow when lit. Mountains also contain springs where groundwater emerges at the surface. Some springs are hot, heated by geothermal activity deep underground. Hot springs in mountains are often associated with volcanic regions. Yellowstone, sitting atop a volcanic hotspot, has thousands of hot springs and geysers. In Japan, mountain hot springs, or onsen, are popular for bathing and relaxation. In Iceland, geothermal hot springs are used for heating homes and generating electricity. Cold springs are more common, fed by rainwater and snowmelt that has percolated through the rock. Mountain springs are often the sources of rivers, and their water is typically very pure, filtered by passage through rock and soil. Many mountain communities depend on springs for their water supply. Waterfalls are iconic features of mountain landscapes. They form where a river encounters a sudden drop, often due to a layer of resistant rock, or the edge of a glacially carved valley. Some waterfalls are enormous. Angel Falls in Venezuela, plunging 979 meters from the edge of a tepui, is the tallest waterfall in the world. Yosemite Falls in California drops 739 meters in 3 sections, its mist visible from miles away. Waterfalls are not static features. They erode the rock at their base, causing the waterfall to migrate upstream over time. The constant pounding of water and the rocks and sediment it carries wear away the rock, creating a plunge pool at the base. Eventually, the rock lip overhanging the plunge pool may collapse, causing the waterfall to move a bit farther upstream. Over geological time, this process can continue indefinitely, with the waterfall slowly eating its way back into the mountain. Niagara Falls, though not in mountains, provides a well-documented example of this process. The falls have retreated about 11 kilometers upstream from their original position at the end of the last ice age, about 12,000 years ago. The rate of retreat was faster in the past, before water was diverted for hydroelectric power, but it continues even today. In mountain waterfalls, where the rock is often harder and the flow more variable, the rate of retreat may be slower, but the principle is the same. The spray from waterfalls creates unique microhabitats. Plants growing near waterfalls are constantly bathed in mist, creating conditions similar to a cloud forest even if the surrounding area is drier. Mosses and ferns thrive in this environment, covering rocks with a green carpet. Some species are found only near waterfalls, adapted to the constant moisture and the cool temperatures created by evaporating mist. Below waterfalls, the turbulent water is highly oxygenated, making it ideal habitat for certain aquatic species. Fish often congregate below waterfalls, and some waterfalls act as barriers, preventing fish from swimming farther upstream. This can result in different fish communities above and below a waterfall, with species below unable to colonize the upstream reaches. This isolation can drive evolution, as populations separated by waterfalls may diverge over time into distinct species. The sound of a waterfall, the constant roar of falling water, is a defining feature of mountain valleys. In some places, the sound is so loud that it drowns out all other noise. In others, it provides a constant background rumble, a reminder of the power of water to shape the landscape. For many people, the sound of a waterfall is deeply calming, a natural white noise that masks other sounds and creates a sense of peace. Glacial caves, formed within or beneath glaciers, represent another hidden aspect of mountain hydrology. Meltwater from the surface of a glacier flows down through cracks and crevasses, eventually reaching the base of the glacier where it flows along the bedrock. This water carves tunnels through the ice, creating caves that can extend for kilometers. The walls of these caves are made of blue ice, compressed over many years and containing few air bubbles, which gives it a deep, intense color. Glacial caves are dangerous and unstable. They can collapse without warning as the glacier moves or melts. The ice shifts constantly, and tunnels that exist one day may be crushed shut the next. Despite the danger, glacial caves are spectacular, with flowing water, ice formations, and an otherworldly blue light that filters through the ice. Some caves are accessible and have become tourist attractions, though visiting them always carries risk. Hot springs in mountains are windows into the geothermal activity beneath the surface. Water seeps deep into the ground, is heated by contact with hot rock or magma, and then rises back to the surface, emerging as a hot spring. The temperature of the water can vary from lukewarm to boiling, depending on the depth it reached and the temperature of the rocks below. Some hot springs are so hot that they are dangerous to touch, while others are perfect for bathing. The chemistry of hot spring water is often unique. As the water is heated underground, it dissolves minerals from the rocks it flows through. When it emerges at the surface, these minerals precipitate out, forming deposits of travertine, silica, or other minerals around the spring. These deposits can build up over time, creating colourful terraces and cones. The colours come from minerals and from thermophilic bacteria and algae that live in the hot water, thriving in conditions that would kill most other organisms. Hot springs support unique ecosystems. Thermophilic microorganisms, adapted to live at high temperatures, form mats and films in and around the springs. Some of these microorganisms are among the most primitive forms of life on Earth, similar to the organisms that lived in Earth's early oceans. Studying them gives us insights into the origins of life and the limits of where life can survive. Some hot springs also support higher organisms like insects, snails, and even fish that have adapted to the warm water. Waterfalls are powerful erosional features. The falling water undercuts the rock at the base, causing blocks to break off, and the waterfall to retreat upstream over time. Some waterfalls migrate upstream by several meters per century. Over geological time, a waterfall can carve a deep gorge, like the Grand Canyon of the Yellowstone, a spectacular chasm carved by the Yellowstone River below the falls. As you drift towards sleep, imagine the hidden life of a mountain. Beneath its surface, water flows through cracks and caves, dissolving rock, carving passages, shaping the mountain from within. On its surface, glaciers creep downward, grinding rock, carving valleys. Rivers tumble down its slopes fed by snow and ice, carrying the mountain to the sea grain by grain. The mountain seems solid, unchanging, but it is alive with movement, with processes that never stop, with forces that have shaped the landscape for millions of years and will continue for millions more. Mountains don't just experience climate, they create it. Their influence extends far beyond their own slopes, shaping weather patterns, guiding wind and rain, and affecting climates across entire continents. Mountains are barriers and generators, dividing the world into wet and dry, warm and cold, windward and leeward. They are sculptors of the atmospheric rivers that bring rain and snow, and they are sentinels that stand in the path of storms. The most direct way mountains influence climate is through orographic precipitation, the process by which moist air is forced to rise over a mountain range, cool, and release its moisture. As air encounters a mountain, it has nowhere to go but up. As it rises, it expands and cools because the atmospheric pressure decreases with altitude. Cool air can hold less moisture than warm air, so the water vapor in the rising air condenses into clouds and eventually falls as rain or snow. This effect can be dramatic. The Olympic Mountains in Washington state receive some of the highest rainfall totals in North America, with some areas getting over 5,000 millimeters of rain per year. Yet just 50 kilometers to the east, beyond the mountains, the land is semi-arid, receiving less than 500 millimeters. The mountains wring the moisture from the air on their western slopes, leaving little for the east. The dry area on the leeward side of a mountain range is called a rain shadow. Rain shadows create some of the world's deserts and dry regions. The Atacama Desert in Chile, one of the driest places on Earth, lies in the rain shadow of the Andes. The Great Basin of the western United States is dry because the Sierra Nevada and Cascade ranges block moisture from the Pacific. The Gobi Desert in Asia is dry partly because the Himalayas prevent moist air from the Indian Ocean from reaching it. Mountains also influence the monsoon, the seasonal reversal of winds that brings heavy rains to much of Asia. During summer, the land heats up more than the ocean, creating a low-pressure zone over the continent. Moist air from the ocean is drawn toward this low pressure, bringing rain. The Himalayas enhance this effect by acting as a barrier that traps the moist air on the southern side, causing it to rise and release its moisture. The summer monsoon brings life-giving rains to India, Bangladesh, and Southeast Asia, and it is influenced heavily by the presence of the Himalayas. Without the Himalayas, the monsoon would be weaker, and the climate of South Asia would be much drier. The mountains also prevent the cold, dry air of the Tibetan Plateau from moving south, keeping northern India warmer than it would otherwise be. The Himalayas are thus a climate barrier of continental scale, shaping the weather and ecosystems of a region home to over 1 billion people. Mountains affect global wind patterns. The jet streams, fast-moving currents of air high in the atmosphere, are influenced by the presence of major mountain ranges. The Rockies and the Andes, both oriented north-south, disrupt the flow of the westerly winds in the mid-latitudes, creating troughs and ridges in the jet stream. These disturbances can influence weather thousands of kilometers away, steering storms and affecting temperature patterns. Mountains also create their own local winds. During the day, the sun heats the slopes, warming the air in contact with the ground. The warm air rises, creating an upslope wind. At night, the process reverses. The slopes cool rapidly through radiation to space, cooling the air in contact with them. The cool, dense air sinks, flowing downslope as a mountain breeze. These daily wind patterns are predictable and can be strong enough to feel. Foehn winds are another mountain phenomenon. When air descends the leeward side of a mountain, it compresses and warms. The rate of warming is about 1 degree Celsius per 100 meters of descent, so air descending 2,000 meters can warm by 20 degrees. This can create sudden, dramatic temperature increases. Foehn winds in the Alps can raise temperatures by 10 to 20 degrees in just a few hours, melting snow and creating spring-like conditions in the middle of winter. Foehn winds can also be dangerous. In places like Southern California, where they are called Santa Ana winds, these hot, dry winds increase the risk of wildfires. Vegetation dries out quickly under the Foehn's influence, and any spark can ignite a fire that spreads rapidly in the wind. Some of the most destructive fires in California's history have occurred during Santa Ana wind events. Mountains also affect the distribution of snow and ice. High mountains capture and store water as snow and ice, acting as natural reservoirs. In winter, snow accumulates. In spring and summer, it melts, releasing water gradually. This storage and release help regulate river flow, providing water during the dry season when it is most needed. In regions like the western United States, snowpack in the mountains is a critical water resource, supplying cities and agriculture far from the mountains themselves. But this system is vulnerable to climate change. As temperatures rise, more precipitation falls as rain instead of snow, and the snow that does fall melts earlier in the year. This changes the timing of water availability, with more water flowing in winter and spring when demand is low, and less in summer and fall when demand is high. The snowpack, which once acted as a natural reservoir, is diminishing, with profound implications for water management. Mountains also influence temperature at large scales. By blocking and redirecting air masses, mountains can keep certain regions warmer or cooler than they would otherwise be. The Alps protect southern Europe from the coldest air masses from the north, making the Mediterranean climate milder. The Rockies similarly influence the climate of the western United States, blocking some of the cold Arctic air from reaching the coast in winter. The presence of mountains can also enhance precipitation in areas well beyond the mountains themselves. When air is forced to rise over a mountain range, it creates waves in the atmosphere that can propagate downwind for hundreds of kilometers. These atmospheric waves can cause clouds to form and precipitation to fall in areas that are not directly over the mountains. This effect, called lee wave clouds, is one of the ways mountains influence weather far from their peaks. Mountains also act as water towers, capturing moisture from the atmosphere and channeling it into rivers. The term water towers refers to the role of mountains in storing water as snow and ice and releasing it slowly over time. About half of humanity relies on water that originates in mountains. The rivers that flow from mountains provide water for drinking, agriculture, and industry to billions of people. The importance of mountains as water towers is most evident in arid and semi-arid regions. In the Middle East, rivers like the Tigris and Euphrates are fed by snow and rain in the mountains of Turkey and Iran. In Central Asia, the Amu Darya and Syr Darya rivers, which once fed the Aral Sea, are sourced from the mountains of the Pamirs and Tian Shan. In the western United States, the Colorado River, which supplies water to 7 states and Mexico, originates in the Rockies. As glaciers shrink and snowpack diminishes due to climate change, the water tower function of mountains is weakening. Rivers that once flowed reliably through the dry season are becoming more variable, with higher flows in winter and lower flows in summer. This poses challenges for water management and increases the risk of drought. Mountains also influence the formation of clouds. Air rising over mountains cools, and if it cools enough, water vapor condenses into clouds. These clouds can be spectacular, forming lenticular shapes that look like stacks of plates or flying saucers. Lenticular clouds form in the lee of mountains when atmospheric waves cause air to rise and fall repeatedly. The clouds form at the crests of the waves and dissipate in the troughs, creating stationary clouds that hang in the sky even as the wind blows through them. Banner clouds are another mountain phenomenon. These form when moist air flows over a peak and cools on the leeward side, creating a plume of cloud that streams from the summit like a flag. The Matterhorn in the Alps is famous for its banner cloud, which forms frequently and gives the mountain a dramatic appearance. Mountains are, thus, not passive features of the landscape. They are active agents in the climate system, shaping weather, storing water, and influencing atmospheric circulation. They are barriers and amplifiers, dividing the world into climatic zones and intensifying the effects of wind and rain. Without mountains, the Earth's climate would be very different. The monsoons would be weaker, deserts would be in different places, rivers would flow differently. The distribution of ecosystems and human populations would be altered. Mountains, in short, help make the Earth the planet we know. As you settle into sleep tonight, imagine the wind rising over a mountain, cooling, releasing its moisture as snow on the peak. Imagine the snow compacting into ice, the ice forming a glacier that flows slowly downward, melting into a river that carries water to the valleys below, where people depend on it for life. Imagine the mountain standing firm against the wind, dividing the wet from the dry, the warm from the cold, shaping the climate for thousands of kilometers around. The mountain is not just rock, it is a climate engine, a water tower, a sculptor of the atmosphere itself. The rocks that make up mountains are more than just the material from which they are built. They are archives of Earth's history, containing clues to ancient environments, past climates, and the movements of continents. They are also repositories of valuable minerals, resources that humans have sought for millennia. To understand mountains fully, we must look at the geology beneath the surface, at the types of rocks, the processes that formed them, and the treasures they hold. Mountains contain a variety of rock types, reflecting the complex processes of their formation. Sedimentary rocks, formed from the accumulation of sediments, are common in many mountain ranges. These rocks began as layers of sand, mud, or the shells of marine organisms deposited on the seafloor or in ancient lakes and rivers. Over millions of years, these sediments were buried and compacted, eventually becoming solid rock. In mountain ranges formed by the collision of continents, sedimentary rocks that were once flat-lying have been folded, faulted, and thrust upward. Layers that formed horizontally now stand vertical or are even overturned. The intense pressures and heat associated with mountain building can transform sedimentary rocks into metamorphic rocks, changing their mineral composition and structure without melting them. Limestone, a sedimentary rock made largely of calcium carbonate, is common in many mountain ranges. It forms from the shells and skeletons of marine organisms like corals, clams, and foraminifera. When you find limestone high in a mountain, you are looking at what was once a seafloor, lifted thousands of meters above sea level by tectonic forces. Fossils in limestone provide evidence of the ancient seas that covered these areas and the life that inhabited them. Sandstone, another sedimentary rock, forms from sand grains cemented together. The sand may have come from beaches, deserts, or rivers. Some sandstones in mountains preserve ripple marks from ancient waves or crossbedding from sand dunes, features that reveal the environments in which the sand was deposited. The colours of sandstone, ranging from white to red to brown, come from the minerals present, especially iron oxides. Shale, formed from mud and clay, is the most common sedimentary rock. It is fine-grained and often soft, easily eroded. In mountains, shale often weathers more quickly than harder rocks like sandstone or limestone, creating slopes and valleys while the harder rocks form cliffs and ridges. Shale can contain fossils of delicate organisms, including plants, fish, and insects, preserved in exquisite detail. Metamorphic rocks form when existing rocks are subjected to high pressure and temperature, causing their minerals to recrystallize. The original rock, whether sedimentary, igneous, or even another, metamorphic rock is transformed into a new rock with different properties. Metamorphism is common in mountain ranges, where the pressures and temperatures associated with tectonic activity are high. Slate is a metamorphic rock formed from shale. It is fine-grained and splits easily into thin sheets, a property called cleavage. Slate has been used for roofing tiles and blackboards for centuries. Schist is a coarser metamorphic rock that forms under higher temperatures and pressures. It contains visible crystals of minerals like mica, which give it a shiny, flaky appearance. Gneiss, pronounced nice, is a high-grade metamorphic rock with alternating bands of light and dark minerals, giving it a striped appearance. Gneiss forms under the highest temperatures and pressures, close to the melting point of the rock. Igneous rocks, formed from the cooling and solidification of magma or lava, are also found in mountains. Granite, a coarse-grained igneous rock, forms deep underground when magma cools slowly, allowing large crystals to grow. Granite is extremely hard and resistant to erosion, making it a common rock in the cores of old mountain ranges. The Sierra Nevada, the Alps and the Rockies all contain large granite plutons, masses of granite that formed deep underground and were later exposed by erosion. Basalt, a fine-grained igneous rock, forms when lava cools quickly at the surface. It is the most common rock in oceanic crust and is also found in volcanic mountains. Basalt is dark in colour, usually black or dark grey, and it is denser than granite. The Columbia River Basalt Group in the Pacific Northwest is one of the largest flood basalt provinces on Earth, covering an area of over 160,000 square kilometres, with layers of basalt up to 2,000 metres thick. Volcanic mountains contain a mix of igneous rocks, including basalt, andesite, and rhyolite, each with different compositions and textures. Andesite, named after the Andes Mountains where it is common, is intermediate in composition between basalt and rhyolite. It forms the bulk of many stratovolcanoes. Rhyolite is similar in composition to granite but fine-grained because it cooled quickly at the surface. Rhyolite lavas are thick and viscous, and eruptions can be explosive. Mountains are rich in minerals, substances with a definite chemical composition and crystal structure. Some minerals are common, like quartz, feldspar and mica, which make up the bulk of most rocks. Others are rare and valuable, like gold, silver, copper and gemstones. The processes of mountain building concentrate these minerals in certain areas, making mountains important sources of mineral wealth. Gold, one of the most sought-after metals, is found in mountain regions around the world. It often occurs in quartz veins, narrow fractures in the rock that have been filled with mineral-rich fluids. As the fluids cool, minerals precipitate, and gold can be deposited along with quartz. Gold deposits are often associated with areas of past volcanic and tectonic activity, where the heat and pressure mobilize the gold and other metals, concentrating them in veins. The California Gold Rush of 1849, which drew hundreds of thousands of people to the Sierra Nevada, was triggered by the discovery of gold in a river that flowed from the mountains. The gold had been eroded from quartz veins high in the mountains and carried downstream, where it accumulated in the riverbed. Similar gold rushes occurred in the Rockies, the Andes, the Urals and other mountain regions, shaping the history and development of these areas. Silver is often found in association with gold, and many mountain regions have been mined for both metals. The silver mines of the Andes, particularly in Bolivia and Peru, were among the richest in the world during the Spanish colonial period. The city of Potosí in Bolivia was built on the wealth of silver from Cerro Rico, a mountain so rich in silver that it was said a bridge of solid silver could be built from Potosí to Spain with the metal extracted from it. Copper is another important metal found in mountains. It is often associated with porphyry deposits, large bodies of igneous rock that contain disseminated copper minerals. The Andes are home to some of the world's largest copper mines, including Chuquicamata in Chile and Toquepala in Peru. Copper is essential for modern technology, used in electrical wiring, electronics, and construction. Gemstones, valued for their beauty and rarity, are also found in mountains. Rubies and sapphires, both forms of the mineral corundum, are found in metamorphic rocks in mountainous regions like Myanmar, Sri Lanka, and the Himalayas. Emeralds, a variety of the mineral beryl, come from Colombia, Zambia, and Afghanistan. Diamonds, formed deep in the Earth's mantle and brought to the surface by volcanic eruptions, are found in some mountain regions, though most come from ancient volcanic pipes in stable continental interiors. Rare earth elements, a group of 17 metals used in high-tech applications like smartphones, wind turbines, and electric vehicles, are also concentrated in certain mountain regions. China controls the majority of the world's rare earth production, much of it from mines in mountainous areas. As demand for these elements increases, the importance of mountain mining regions grows. Mining in mountains has environmental costs. Open pit mines scar the landscape, removing entire mountaintops. Tailings, the waste material left after ore is processed, can contaminate rivers and soils with heavy metals. Acid mine drainage, caused by the oxidation of sulfide minerals in mine waste, can acidify streams and kill aquatic life. Balancing the economic benefits of mining with the need to protect mountain ecosystems is an ongoing challenge. Mountains also contain fossils, the preserved remains of ancient organisms. Fossils provide evidence of past life and environments, allowing scientists to reconstruct the history of life on Earth. Some of the most important fossil discoveries have been made in mountains, where uplift and erosion expose rocks that would otherwise remain buried. The Burgess Shale in the Canadian Rockies is one of the most famous fossil sites in the world. Discovered in 1909, it contains exceptionally well-preserved fossils from the Cambrian period, about 508 million years ago, a time when complex life was diversifying rapidly. The fossils include soft-bodied organisms that are rarely preserved, giving a unique window into the early evolution of animals. The Himalayas contain fossils of marine organisms, including ammonites, ancient cephalopods related to modern squid and octopuses. These fossils are found at high elevations, evidence that the rocks now forming the mountains were once part of the seafloor. When India collided with Asia, the seafloor was crumpled and lifted, carrying the fossils to the roof of the world. Dinosaur fossils have been found in mountain regions around the world. In Patagonia, the mountains have yielded some of the largest dinosaurs ever discovered, including Argentinosaurus, estimated to have weighed 70 to 100 tons. In China, fossil sites in mountainous regions have produced feathered dinosaurs, providing critical evidence for the link between dinosaurs and birds. The study of mountain geology is not just about understanding the past. It also has practical applications. Engineers need to understand the rock types and structures in mountains to design roads, tunnels, and dams. Geologists study mountain rocks to predict the location of mineral deposits and to understand hazards like landslides and earthquakes. The knowledge gained from studying mountain geology helps us use mountain resources responsibly and live safely in mountain regions. As you rest tonight, imagine peeling back the surface of a mountain to reveal the layers beneath. See the folded and faulted rocks, once horizontal, now twisted and tilted by unimaginable forces. See the granite, formed deep underground and slowly exposed by erosion. See the fossils, the ancient shells and bones preserved in stone, telling stories of seas that no longer exist and creatures long extinct. The mountain is not just a pile of rock, it is a library, a treasure chest, an archive of Earth's history written in minerals and stone. Mountains are changing faster now than at any time in recent history. The climate is warming, and mountains, sensitive to even small changes in temperature, are responding. Glaciers are melting, ecosystems are shifting, permafrost is thawing, the changes are visible, measurable, and accelerating. Understanding what is happening to mountains and what it means for the future is one of the most urgent tasks facing scientists and societies today. Glaciers are the most visible indicator of climate change in mountains. Around the world, mountain glaciers are retreating. Data from the World Glacier Monitoring Service shows that reference glaciers have lost ice equivalent to about 27 meters of water since 1970. That's like slicing nearly 30 meters off the top of each glacier. The rate of loss has accelerated in recent decades. In the 1980s, glaciers lost an average of 871 millimeters of thickness per year. By the 2000s, that had increased to 500 millimeters per year, and it continues to accelerate. Some glaciers have already disappeared. In Glacier National Park in Montana, there were 150 glaciers in 1850. Today there are fewer than 30, and most of those are small remnants that will likely vanish within a few decades if current trends continue. The glaciers of the Pyrenees, the Alps, the Rockies, and the Andes are all shrinking. In the tropics, glaciers on mountains like Kilimanjaro and in the Andes are losing ice even faster, with some projected to disappear entirely within this century. The loss of glaciers has cascading effects. Glaciers store water as ice and release it slowly as melt, providing a steady supply of water to rivers during the dry season. As glaciers shrink, the amount of water they can store decreases, and the timing of water release changes. Eventually, a glacier reaches peak water, the point at which meltwater reaches its maximum volume. After peak water, as the glacier continues to shrink, the amount of meltwater decreases each year. Many small glaciers have already passed peak water, and larger glaciers are approaching it. This has serious implications for water supplies. In the Andes, communities rely on glacial meltwater for drinking water and irrigation. As glaciers disappear, these communities face water shortages. In the Himalayas, hundreds of millions of people depend on rivers fed by glacier melt. The long-term loss of glaciers threatens their water security. In the western United States, snowpack and glacier melt provide water to cities and farms in arid regions. As these sources decline, competition for water intensifies. Permafrost, ground that remains frozen year-round, is thawing in mountain regions. Permafrost is widespread in high mountains, even in the tropics, wherever temperatures remain below freezing. It acts like glue, holding rock and soil together. When it thaws, the ground becomes unstable. Slopes that were stable for thousands of years can suddenly collapse, triggering landslides and rockfalls. Thawing permafrost is increasing the frequency and size of mountain hazards. Rock avalanches, where large sections of a mountainside collapse and tumble down the slope, are becoming more common. In 2017, a massive rock and ice avalanche in the Himalayas killed 9 people and destroyed a village. Similar events have occurred in the Alps and the Andes. The thawing of permafrost is one factor contributing to this increase. The tree line, the elevation above which trees cannot grow, is shifting upward in many mountain ranges. As temperatures warm, areas that were once too cold for trees are now warm enough trees are, colonizing alpine meadows and tundra, changing the landscape and the ecosystems. This might seem like a positive change, but it has mixed effects. Trees can provide habitat for some species, but they also shade the ground, reducing habitat for alpine plants that need full sun. As trees move up, alpine ecosystems shrink, and species adapted to alpine conditions have less room to survive. Alpine plants are particularly vulnerable to climate change. They are adapted to cold, and many are endemic, found only on specific mountains or even specific peaks. As temperatures warm, these plants must move upward to find cooler conditions. But mountains have finite height. Eventually, there is nowhere left to go. Plants at the summit are pushed off the top, so to speak, into extinction. This is called summit trapping, and it is a growing concern for alpine biodiversity. Some alpine species are already showing signs of stress. Populations are declining, and ranges are shrinking. In the Alps, certain alpine plants have moved upward by hundreds of meters over the past century. In the Rocky Mountains, similar shifts are documented. The pace of change is faster than many species can adapt, and the risk of extinction is real. Animals in mountains are also affected. Species like the pika, a small mammal that lives in alpine environments in North America, are losing habitat as temperatures warm. Pikas are adapted to cold and cannot tolerate heat. They are restricted to high elevations, and as the climate warms, they are moving higher. But on many mountains, pikas are already near the summits, and there is no higher to go. Some populations have already disappeared from lower peaks. Mountain ecosystems are shifting upward, but the species in them are not all moving at the same pace. Plants may move more slowly than the insects that pollinate them, or the herbivores that feed on them. This can disrupt ecological relationships, with mismatches in timing or location leading to declines in both plants and animals. The complex web of interactions that sustains mountain ecosystems is being strained by rapid change. Snow is arriving later and melting earlier in many mountain regions. The length of the snow-covered season is decreasing. This affects not just ecosystems, but also human activities. Ski resorts at lower elevations are struggling, with shorter seasons and less reliable snow. Some resorts have closed. Others are investing in snowmaking equipment, which is energy-intensive and requires large amounts of water. The changes in snow also affect water supplies. Snow acts as a natural reservoir, storing water through the winter and releasing it in spring and summer. As temperatures warm, more precipitation falls as rain instead of snow, and the snow that does fall melts earlier. This changes the timing of water availability. Rivers have higher flows in winter and early spring, when demand is low, and lower flows in summer and fall when demand is high. This mismatch complicates water management and increases the risk of drought. Glacial lakes are growing and multiplying as glaciers retreat. These lakes form in depressions left by the glacier, or behind moraines, ridges of rock debris deposited by the glacier. While these lakes can be beautiful, they also pose hazards. If the moraine or ice dam that holds the lake fails, the water can burst out in a catastrophic flood. These glacial lake outburst floods, or GLOFs, can travel far downstream, destroying everything in their path. The number of glacial lakes has increased dramatically in recent decades as glaciers retreat. In the Himalayas alone, there are thousands of glacial lakes, and many are growing. Some are monitored because they are considered high risk, meaning a failure could affect populated areas downstream. Efforts are being made to reduce the risk, such as draining lakes or reinforcing moraine dams, but the task is immense and the resources limited. Mountain communities are on the front lines of climate change. They are witnessing changes that people in lowlands may not yet see. They are adapting, but adaptation has limits. Some communities are relocating, moving away from areas at risk of landslides or floods. Others are changing their livelihoods, moving away from agriculture or tourism that depends on snow. The loss of glaciers, which are culturally and spiritually significant to many mountain peoples, is a profound loss that goes beyond water supply or tourism. The future of mountains depends on how much the climate continues to warm. If global temperatures are limited to 1.5 degrees Celsius above pre-industrial levels, many glaciers will still disappear, but some will survive. If warming exceeds 2 or 3 degrees, most small glaciers will be gone by the end of the century. The Himalayas could lose 2/3 of their ice. The Alps could be nearly ice-free. The consequences for water supplies, ecosystems and communities would be severe. Even with aggressive action to reduce greenhouse gas emissions, some changes are already locked in. The glaciers that have already lost mass will not regrow quickly, even if temperatures stabilize. Ecosystems that have shifted upward will not easily move back down. Permafrost that has thawed will not refreeze. The mountains of the future will be different from the mountains of the past, and adapting to these changes will be one of the great challenges of the coming decades. Yet there is hope. Mountains are resilient. They have endured ice ages and warm periods before. Life in mountains has adapted to changing conditions over millions of years. While the current pace of change is faster than anything in recent history, mountains will persist and life will find ways to survive. The question is not whether mountains will endure, but what they will look like, and whether the ecosystems and communities that depend on them can adapt quickly enough. As you rest tonight, think about the glaciers, slowly melting in the warmth of a changing climate. Think about the alpine meadows shifting upward meter by meter. Think about the rivers changing their rhythms and the communities adapting as best they can. Mountains have seen change before, but never so quickly. They are changing now in our lifetimes in ways we can see and measure. And how we respond to these changes will shape not just the future of mountains, but the future of all who depend on them. And so, we have travelled together through the world of mountains, from their violent births in colliding continents to their slow erosion over eons. We have climbed from warm valleys to frozen peaks, passed through forests and tundra, and stood in the presence of ice and rock. We have seen how mountains shape climate, harbour life, and hold the history of Earth in their stone. We have learned that mountains are not eternal, but are always changing, always moving, always in conversation with the forces that created them and the forces that are wearing them down. Mountains are among the most remarkable features of our planet. They are monuments to the power of tectonics, to the slow grinding of continents, to the patience of geological time. They are also refuges, places where life has found ways to thrive in conditions that test the limits of survival. They are water towers, feeding rivers that sustain billions of people. They are climate engines, shaping weather and ecosystems across entire continents. But more than all of this, mountains are witnesses. They have stood through the rise and fall of species, the opening and closing of oceans, the breaking apart and reassembling of continents. They have seen life emerge from the sea, forests spread across the land and ice sheets advance and retreat. They have seen the birth of humanity and the spread of our species across the globe. They will outlast us, standing long after we are gone, weathering whatever the future brings. Tonight, as you drift toward sleep, let the mountains be your companions. Imagine their peaks rising above the clouds, bathed in moonlight or starlight. Imagine the silence of a high alpine meadow, broken only by the whisper of wind through grass. Imagine the patience of stone, the slow wearing away of peaks, the inexorable grind of time. Let these thoughts carry you gently into rest, knowing that somewhere a mountain is standing, as it has for millions of years, and will for millions more. If you've enjoyed this journey through the mountains, if these gentle explorations have helped you find a moment of peace, please consider liking this video and subscribing to the channel. It helps others discover this space, one restful night at a time. There are more journeys to come, more stories to tell, more wonders of the natural world to explore together. Until then, rest well. Let your breathing slow, your muscles relax, your thoughts drift like clouds over distant peaks. The mountains are there, always standing, patient and strong beneath the turning stars, and you are here, safe, warm, drifting gently towards sleep. Good night.